Hi, this video is going to look at periodicity from the A-level OCR chemistry specification. It's going to go through electron configurations as you go across a period. It's going to look at ionization energy as you go across a period, and it's going to look at melting point and look at some of the trends of these two. So the first thing we look at is electronic configurations, because these come in quite important later on. We're looking at some of the properties. We're going to look at period 2. So period 2 all have a 1s orbital, and then they fill up the 2s and the 2p. So first of all, we're going to have lithium, which is going to be 1s2. That was in the previous subshell. It's the s before this period, and then its electron goes into that 2s1. Next up, beryllium, 1s2 again, and now it is going to put its second electron into there. Now boron goes into this orbital on the 2p. So that gives me 1s2, 2p, missing out 2s2, 2p1. And so there's a sudden change here. We've gone from s block elements, so lithium, beryllium, both final electron in the s subshell. So these are s block elements, and they're in that first two groups on the periodic table. Boron goes across into 2p1, so that's across on the right hand side of the periodic table in the p block. Now carbon, its next electron goes there. It'd rather go into an empty orbital. There's slight repulsion between the electrons in the same orbitals, so it's lower energy for it to go into its own orbital. So this is 1s2, 2s2, 2p2, and nitrogen fills out, or doesn't fill them all, but it puts one electron into all the orbitals. Now oxygen comes back, and it has no choice. It has to go into that orbital. There's no other space for it, even though this electron is pushing this electron away. They're both negatively charged, so there's some repulsion there, and that's important later on. We'll look at some of the properties. Fluorine then is 1s2, 2s2, 2p5 with its fifth electron going into that middle orbital, and then neon fills everything, which makes it nice and stable. So that's how electrons fill in as we go across. So we have two important little bits to remember. First of all, there's a jump between 2s filling and 2p starting. So when beryllium goes to boron, we start a new subshell. And also, each of these go into separate orbitals before oxygen comes along, and then oxygen doesn't have a choice. It has to double up in an orbital. So that's electron configurations. Next up, we're going to look at ionization energies. And we can get a definition down first of all, and that's the removal of 1 mole of electrons from 1 mole of gaseous atoms. So an equation for this would be if we take any element and work out, I'm sure it's first ionization energy, it'd be X, and we need it to be a gas. And this is going to go to X plus gaseous plus an electron. So each atom in a mole of atoms is going to lose 1 electron. And if we look at the trend across a periodic table, prepared this a little bit earlier, and this is first ionization energy. So lithium is quite low down. It's only got 2 protons holding onto its outer electron, so it can't grip onto it very well, so the electron can get away quite easily. We get a jump up to beryllium. And so beryllium has got 4 protons and the same amount of shielding, so it can hold on to its electron a bit better than beryllium, so we need more energy to release it. We do get a drop now. So boron drops down. Now this is because here we've got our S blocks, now it's going to a P block. And now this P block, a bit higher in energy, it's easier to remove an electron from the P block. So we looked at the electron configurations of beryllium and boron. We saw boron gone across into that P block, easier to remove an electron from there. Then carbon goes a little bit up, so a bit higher in ionization energy. Nitrogen, again, higher in ionization energy, but we get a drop here to oxygen. And that's because despite oxygen having more protons and having the same amount of shielding, it's now doubled up in its P block. So remember its P block. Nitrogen had a P block that looked like that. Oxygen, that 4th electron went into the first orbital again in that P block, and those electrons repel each other, so it's easier to remove that electron. Then fluorine goes up a bit more, and then neon way up at the top. So that is first ionization energies, and this pattern in periodicity is the same. This is period 2, it's the same in period 3 for the same reasons. We get the drop here when we go into the P block, we get the drop here because of pairing up electrons in orbitals. So the final thing we need to look at is the melting points. And the melting points requires a little bit of knowledge to be stored and remembered. So this is the melting points as we go across period 3. So sort of general rise with a big jump up to silicon, then big drop, and we get kind of phosphorus quite low down, sulfur a little bit higher, and then a drop, and then a big drop. Now this is due to the type of bonding they have. So first of all, we've got sodium, magnesium, and aluminium, and they're all metallic atoms. So when they come together and form like a compound, it's all metallic. We get a general increase in melting point because the sodium forms plus ions, magnesium 2 plus ions, aluminium 3 plus ions. So we get a stronger kind of magnet attracting the electrons. Also, they get a bit smaller as we go across as well. They get contracted, so the distance between sodium and its electrons is greater. Sodium and the electrons is greater than aluminium and its electrons, and this is the bond that holds it together. So if you can break that bond, then it melts. Aluminium holds together a bit more because they're closer. Silicon is the big one, and that's because silicon is giant covalent. So trillions and billions of silicon atoms all joined together by strong covalent bonds. So very, very difficult to get to melt and break those bonds down. Now phosphorus, sulfur, chlorine and argon, these are all simple covalent. So the only thing holding these together are the London dispersion forces, or induced dipole bonds, van der Waals forces, however you want to call them. And they're determined by the number of electrons. So you need to know how each of these likes to exist in its elemental form. And phosphorus is P4. Sulfur exists as S8, chlorine as Cl2, and argon just by itself. So we then, if we looked at the number of electrons we've got here, phosphorus at P4 has 60, because it's got 15 electrons in one atom of phosphorus, so 4 will have 60. Sulfur is 128,
16 times 8. Done it very quickly in my head. I hope that worked out well. So 128 electrons in sulfur. So you can see straight away that more electrons, greater induced dipole forces, and we see that in their melting point. Sulfur has a higher melting point. Chlorine, Cl2, has just got 34 electrons, so that's where we get the drop here. And argon, just existing as an atom, has just 18 electrons, so it has the lowest melting point because it's got the weakest induced dipole bonds. And that is a very quick tour through periodicity.